Consider formate, all right, which is the anion formed when formic acid loses an H. All right, so one of those H's came off of an O. The other H is connected to the central carbon. Write one or more appropriate Lewis structures for this ion. All right, so this is the constitution of the molecule, right? This is a central carbon. Everything's connected to it. We count up the valence electrons, 12 electrons for the oxygens, 4 for the carbon, 1 for the hydrogen, and 1 extra one because it has a -1 charge. We have 18 electrons to play with, 6 electrons to bond everything together. All right, so those are the bonded pairs. And that gives us 12 electrons yet to be assigned, right? So they go to the oxygens first to complete their octets, and we're done. We have an incomplete octet for the carbon. All right, so this is going to be a resonance structure. Either one of these oxygens could donate an electron to the double bond. So I could have a double bond on the number 1 oxygen or a double bond on the number 2 oxygen. So we write both Lewis dot structures, right, with a formal charge on the single bonded oxygen, and put a double arrow to indicate resonance. What would you predict the bond angle for not the bond angle, what would you predict the bond length to be for between the carbon and the oxygen in formate relative to those of CO2? All right, so let's do the Lewis dot structure for carbon dioxide. Right, we've got a central carbon, we count up the electrons, we put them in. We have an incomplete octet for the carbon. So both of the oxygens are going to have to donate an electron pair to make a double bond, right? Oxygen can only bond to 2 things, right? 2 half-filled orbitals, so 2 bonds. So this gives us 2 true double bonds between the carbon and the oxygens. Whereas with formate, that's not really a true bond on either of the oxygens, right? It's a bond and a half, right? The double bond is delocalized actually over all 3 atoms, right? The carbon and the 2 oxygens. So the bond length between the carbon and the oxygens in formate is going to be a little bit longer because it's part single bond, not completely double bond. Draw Lewis dot structures for the following ions which do not obey the octet rule. All right, so nitrogen monoxide, when you count up the electrons, you get an odd number of electrons, right? So right there, you're going to break the octet rule. So we don't have too many of these. This is the one example you have to know for the AP exam. So when I count up the electrons, I got 11. I bond things together. That's 2 electrons, 9 have to be assigned. They go to the oxygen first, and any leftovers go to the nitrogen. And that's it. This is all you can do for this structure. So you've got a formal charge of +1 on the nitrogen, a formal charge of -1 on the oxygen, and this would be the Lewis dot structure for nitrogen monoxide. Right, you're breaking the octet rule. Boron trifluoride. All right, so when you count up the electrons, you have 24, 6 to bond everything together, 18 to be yet to be assigned. Now, the fact is, I can't double bond with fluorine. Fluorine only has a single half-filled orbital. So this is it, all right, for boron trifluoride. You're breaking the octet rule. You don't make a double bond here to complete the octet for the boron because fluorine can't. Fluorine can only bond to something, bond to one thing with a single bond. So this would be the complete Lewis dot structure for boron trifluoride. This ICl2 minus anion, right? We have 1 extra electron because we have a negative charge. That gives me 22. 4 electrons to bond everything together. 18 electrons yet to be assigned. So chlorine's more electronegative than iodine. So 12 of those electrons are going to go to completing the octet for the chlorine. That leaves me 6 yet to be assigned. So they're going to be put around the central iodide. So you're going to have 2, 4, 6, 8, 10 electrons around that iodide. Again, you're going to be breaking the octet rule with 2 bonded and 3 lone pair around the iodide. -1 formal charge on the iodide. Doing this OP Br3 molecule. Oops, let me go back one. We put the electrons in. We have a formal charge of +1 on the oxygen and a +1 formal charge on the phosphorus. This is perfectly acceptable, but sometimes what happens with these, with something like central phosphorus can break the octet rule by having more electrons around it. So to minimize formal charge, we put a double bond between the phosphorus and the oxygen. We now have 10 electrons around the central phosphorus, and we're breaking the octet rule here. So frankly, this is the more stable structure. It doesn't have formal charge in it for this molecule. So again, you're breaking the octet rule around the phosphorus. This would be a tough one. Looking at E, this is more conventional. Count up the electrons. You have 36 to play with. Bond everything together. That's -8. 28 electrons yet to be assigned. So 24 of them go to completing the octets for the fluorine. And this gives you 2 extra pair of electrons around the xenon. Again, we're breaking the octet rule here by having 2, 4, 6, 8, 10, 12 electrons around the central xenon. But xenon does this, breaks the octet rule sometimes. All right, with number 70, we're supposed to get an estimation for the heat change when, what is that? Tribromomethane reacts with chlorine to make tribromochloromethane and hydrogen chloride. All right, so what you can do with bond dissociation energies, right? The energies required to break the bonds is you can add up the bonds broken, all right? Those are going to be endothermic, right? You got to put energy in to break bonds. Add up the bonds formed, which are going to be exothermic. Those are going to be releasing. Whenever you make a bond, you release heat. And you can subtract the bonds broken from the bonds formed, and you can get an estimation as the delta H, right? Just like we did in Chapter 6, where we had to look up the heats of formations of things and plug them into Proximized reactants. We can get an estimation using bonds broken minus bonds formed. So, with that said, I look at the chart. What are the bond energies for breaking a carbon-hydrogen bond, a carbon-chlorine bond, a carbon-bromine bond, and a hydrogen-chlorine bond? Recognizing that these are estimations, right? I mean, there's like, for example, a carbon-hydrogen bond is changes locally depending on what else is attached to the carbon. So this 413 for breaking a carbon-hydrogen bond is an estimate. So with these estimates, we can get an estimate for what the heat change is going to be. All right, so the way to do these is try to be elegant, right? You try to break as few bonds as possible and try to make as few bonds as possible. So I can see right off, if I break that hydrogen off, I'm going to have 3 bromines connected to a carbon piece. If I break the chlorine-chlorine single bond, I'll have individual chlorine atoms to attach. So it's going to cost me 413 to break that hydrogen off, 242 to break the chlorine-chlorine single bond. Now on the other side, I can take one of those chlorines and attach it to the carbon, right? That's going to release 328 kilojoules. And I can attach that broken off hydrogen and broken off chlorine together to make a hydrogen-chlorine molecule. And that's going to release for 31 kilojoules. So I plug it into bonds broken, I should say. Some of the bonds broken minus the sum of the bonds formed. So it's a different equation. So I just sum up the delta, the sum of the bond dissociation energies for the bonds broken, and subtract from that the sum of the bonds formed. And the negative sign changes those bond dissociation energies in the products or the bonds formed to negative values. So just sum up the bond dissociation energies and subtract. So this is an exothermic process. I'm releasing more heat, making the bonds than I am putting in to break the bonds. So I get an estimate as to what the heat change is going to be. So another one. Again, we're trying to be elegant here. How can I go from the reactants to the products in the simplest way? So I can see right now I'll have a C2H4 chunk. If I can chop those SHs if I can break the SC bonds and get those SHs off of there. If I break the two hydrogen bromine bonds, right, it's times 2, I'll have H's to reattach to those S's to make the two dihydrogen sulfides I need to make, and then I can reattach those bromines to my chunk in the middle. So I'm going to break these bonds, right? I'm going to 259 to break both of those sulfurs off of those carbons, and 2 times 366 to break the two hydrogen bromine bonds. On the other side, I'm going to reattach those bromines. That's going to release 276 kilojoules apiece, and I'm going to attach those two hydrogens that I broke off of those bromines to the SHs to make dihydrogen sulfide. So I plug it in. Sum of the bonds broken minus the sum of the bonds formed, and I can get the change. All right, so this is an endothermic process. Now, technically, I could pull everything apart and then put everything back together, and I should get the same answer. But there's more mistakes doing it that way. It really is simpler to look for the least number of bonds broken and the least number of bonds formed in order to turn those reactants into products. So again, I've got an N2H4 reacting with Cl2. I want to break that NN bond, right? There is no NN bond on the other side, right? So break that NN bond, and that'll give me 2 NH2 groups. If I break the ClCl bond, right, and that'll give me the Cls to attach. So break the NN bond, break the ClCl bond, make 2. I have it shifted over. I didn't mean to put it there. I want it between the N and the chlorine, right? So I'm making a... yeah, let me shift it over. Later. Oh, no, don't want to do that. Oh, no, I don't want to do that. Okay, I want to do this. That's all I want to do. Okay, let's go back. So, play. Break these bonds, make 2 of these bonds. All right, and sum them up, right? Bonds broken minus bonds formed. This turns out again to be, it's in the middle there. Is it endothermic? Is it exothermic? It's, you're not releasing much, requiring much heat in order to go from reactants to products.